Sound pressure level, SPL, is a measure of how much the ambient air pressure is disturbed by a sound wave. It's not a measure of how loud a sound is, but it's related, and so we often use SPL measurements to make sure we're not damaging people's hearing or disturbing the neighbors. There are a bunch of different ways to measure SPL, different metrics, and so for an SPL measurement to be meaningful, we have to include some information about how it was measured. A numerical dB value on its own is too vague to tell us anything. One important thing to know is the frequency weighting curve used by the measurement. The tonal response of human hearing varies pretty significantly depending on level, particularly in the low frequencies. You may have heard of the equal loudness contours, which describe this. This is one of the reasons that SPL doesn't always correlate with our perception of loudness. Most SPL meters offer frequency weighting curves intended to mimic our hearing response at various levels. In practice, this isn't very effective, but as we can see, the varying roll-offs can make quite a big difference in the measurement, particularly if the signal has a lot of low-frequency energy, like at a music concert. Most meters offer a choice of A weighting or C weighting, and you might see an unweighted measurement referred to as Z weighting. A weighting is important because it's specified in a lot of noise exposure limits. So when we make an SPL measurement, we need to make sure to include a suffix to indicate which frequency weighting was used. For example, it's acceptable to indicate an A-weighted measurement as either dB-SPL-A or simply dBA, or even dBA without the parentheses if you really want to save a couple keystrokes. Another thing we have to consider is the length of time incorporated into the measurement. A transient event, like a gunshot or a snare drum hit, will have a high peak value, but a lower value over time because of the quiet periods in between. Most handheld meters offer SPL fast, with an integration time of 1/8 of a second, and SPL slow, with an integration time of 1 second. We can see here how the integration time affects the measurement. Most noise exposure limits are specified as single numbers, which makes sense when dealing with relatively steady-state noise sources like industrial machinery. But what about a concert? Live music can be pretty dynamic, so when we want to get a better idea of average level over time, we can use a metric called equivalent sound level, or LEQ for short. It measures the SPL over a specified amount of time and averages to a single number decibel equivalent. The number of minutes in the average is indicated in the suffix, for example, LEQ10 or LEQ15. LEQ measurements are really helpful for regulating sound levels at concerts because the longer measurement periods allow the sound engineer to mix a dynamic show that has loud moments and quiet moments while still keeping the equivalent exposure to a safe level. Here's an SPL history timeline of a 1-hour concert showing the SPL fast and slow metrics like you might see on a handheld meter. The LEQ1 metric shows a better idea of the dynamic contour of each song, and the LEQ10 allows us to clearly see an equivalent SPL for the entire show, determine whether it falls within exposure guidelines, or simply help the mix engineer achieve night-to-night consistency. So now that we've looked at both the frequency domain and the time domain considerations of SPL measurement, it's important to remember that we usually need both pieces of information to make a meaningful statement about an SPL measurement. All the metrics we just looked at, SPL fast, SPL slow, and LEQ, can have different frequency weighting filters applied as well. Let's return to the drum set. If we compare the A-weighted and unweighted versions of the SPL fast metric, we can see that they differ in this case by about 10 decibels. That's because the low-frequency roll-off of the A-weighting filter doesn't respond to the energy from the kick drum. Same thing with the slow metrics. The longer integration time means less variation over time, and the A-weighted trace still comes out about 10 dB lower because of the lack of low-frequency energy in the measurement. And here's LEQ1 in Z weighting, C weighting, and A weighting. We indicate those as LEQ1, LCEQ1, and LAEQ1. Note that the difference between A weighting, C weighting, and unweighted measurements will depend heavily on the amount of low-frequency energy in the signal. For speech signals having little low-frequency content, the difference will be small. For example, here's an LEQ1 timeline for the last few minutes of this narration, showing both unweighted and A-weighted. And how about that concert? The management team at this concert set a goal of complying with the recommended exposure limit established by the National Institute of Occupational Safety and Health, which is 94 dBA for a 1-hour exposure. A handheld meter measuring SPL fast or slow doesn't give a good answer here, even with A-weighting filters in place. Looking at LEQ10 gives us a good picture of the average level of the event, and with A weighting, the level sits comfortably right around 94 dB SPL. The mix engineer was able to create some loud, exciting moments, along with some quieter, more intimate ones, and the show was at a safe equivalent level, so no one gets hurt and everyone goes home happy.